Thanks for having us today in this webinar. My name is Besmira Nushi. I'm a researcher at Microsoft Research, and I'm here today together with Marnoor Sameki, who is a program manager at Azure Machine Learning. And together we're going to give you an introduction and a hands-on sort of demo and tutorial on our latest release, which is the Responsible AI Dashboard. And this is a tool for accelerating and operationalizing responsible AI. And you'll see that it brings together several other efforts that we have presented in the past at ODSC. But now we are going to show you how you can use through a single pane of glass all these tools together and be able to run end-to-end machine learning debugging and decision making. So our agenda for today is going to be the following. We're going to go very quickly through the responsible AI principles at Microsoft and more broadly, the tools that we have introduced in the past. And then we'll introduce the responsible AI dashboard, the main concepts around it. And in order to make all of this a little bit more concrete, we're going to give you a demo on the two main areas that the dashboard covers, which is machine learning model debugging and causal decision making. And we will be taking questions towards the whole presentation, but perhaps maybe during the whole presentation we'll take like the shorter questions, and if we have something longer to discuss, or if you want to share some of your experiences in using these tools or other tools in the past, feel free to share with us, either in the chat or in the question tab. With that, I also want to thank you for being with us here today, in that we know it's like a pre-holiday time, so we appreciate the attendance and the interest in this talk. So before I start, I want to also thank the whole team that has worked in this effort. This is a true collaboration across different design, engineering, and research teams at Microsoft and Azure, Microsoft Research and Azure Machine Learning. And you will see that many of the components that we're going to present today are coming from different areas of labs at Microsoft Research and different teams within Azure Machine Learning that work on operationalizing these tools and making them part of a whole ecosystem. So let me first start by challenging one of these perhaps common notions that we see today, that responsible AI is perhaps just a nice to have concept or something that you think about as an afterthought after you have built the whole AI system or machine learning model. And in order for us to challenge this notion and to really explain why responsible AI is instead about excellent machine learning engineering and about responsible innovation and why it is a must-have, we are going to look at this problem from a machine learning engineer and practitioner perspective. And we are going to show that only through the usage of certain, practical tools and guidelines and principles, it is possible to build high-quality products that work for everybody and that can actually bring real value to the society. So here is a very quick overview to the Microsoft's responsible AI principles. You might have seen this in the past, but these principles relate to aspects of AI systems and deployments, such as fairness, reliability and safety, privacy and security, inclusiveness, transparency, and accountability. Now, many of these principles may not be new to you. Many other companies have similar principles, maybe phrased in a slightly different way, but at the end of the day, all of them sort of care and highlight this importance of being able to include many different stakeholders in the build-up of machine learning systems. And one very practical need that comes up is the need for being able to first evaluate system performance across different demographic groups, key use cases, and operational factors. So similarly to when we build a bridge or another software system that maybe is not machine learning oriented, or anything that has to do with innovation, generally we would like to try this this product and be able to tell to customers and users when the model works and when it doesn't, right? When the innovation works and when it doesn't, what are its limitations? Is it inclusive? Does it work for different use cases, and so on and so forth? And this is at the core of any principle that that we care about, just that the problems that may originate from the violation of a certain principle may be reflected in the real world, for example, as fairness issues or as safety issues with the use case. So this is the set of principles, and often when we talk about this internally in the company, but also externally with open source communities, one of the main questions that arises is, how do we put this in practice? How do we make sure that all these principles are actually satisfied and we build high quality products? And in fact, this transition from principles to practice is not a a straightforward one. In fact, on December 7, we had an overall event at Microsoft that showed guidelines and tools, including the Responsible AI dashboard, to illustrate how do we put these principles into practice. So I'd suggest you take a look at that as well. We see that based on many surveys and studies that we have ran in the past and we have updated in the last few years, we see that actually bringing these principles to practice is a challenging task, mostly because of the lack of tools, mostly because all these different principles have different requirements, and it's hard to put them all together into one single dashboard. One very interesting study that came out of Microsoft's research a few years ago is software engineering for machine learning. I suggest you take a look and to really understand what are the low-level challenges that developers face every day in order to apply these principles. So because of, when we look back 5 years ago, one of the main challenges that we saw, especially in this study, is the fact that there is a lack of tooling when it comes to proper evaluation of machine learning, and especially for responsible AI. And so many teams in collaboration with Azure and research, we saw that there is a need for the availability of these tools. And so several tools came out of these collaborations. I'm going to mention some of them here, but there is a lot more, especially, even outside of Microsoft. For example, InterpretML is a tool for generating explanations for different models, and also for building models that are transparent by design. Error analysis is a tool for understanding better model errors, chopping and slicing the data according to these model errors, and checking whether there are cohorts with higher error representation. Fairlearn is a tool that is laser focused on fairness in order to identify and mitigate fairness issues in models. DICE, we're going to give an overview later for generating counterfactual explanations on different instance levels in the model. And then EconML and DoY focus on causal inference. And then finally, backward compatibility in machine learning is a tool that cares about model comparison, but also makes sure that we train models that do not make new errors and do not introduce regress when we update our models. Because eventually a good model is one that gets updated over time and is improved and basically maintains customer trust. So as you can see, there's a whole rich ecosystem here, and not to mention, other perhaps efforts that are still ongoing and that wait for more customer support. Now, another challenge that we noticed after working on all these tools is the fact that there exists tool fragmentation, in that many of these tools, because the area is so new and it's moving so fast, many of these tools do not interact with each other. If you are a machine learning engineer, you have to use them separately and exchange data from one tool to the other. So we noticed the following challenges. First of all, there is a learnability challenge, in that if these tools are not presented together, or they are not it is not possible to access them through a single dashboard, then machine learning engineers may not, they will have a higher learning curve because they will need to learn how to use all these tools altogether. And then there is a discoverability issue in that perhaps even though you may be able to learn these tools fast, it is not possible to know where everything is, or even to be aware that there exists a tool that maybe will solve your problem. And often what we see in the user studies is that practitioners, instead of, when they are not exposed to this information, sometimes they go ahead and they build their own tool, and they try to build all this spaghetti of scripts that can solve their problem that maybe is just a one-off solution, and then they need to build the same solution again when they are solving another problem. And then the third challenge, or sort of like desiderata for doing tool integration, is this ability between tools to share insights and data. So as I mentioned earlier, there are different aspects of responsible AI principles, but these are not, very well separated from each other. In practice, all of these principles may be applicable to a product, and one may want to move, from looking at the problem from a fairness lens to an interpretability lens. So being able to share data that comes out from one tool and put it back to another tool in order to get the best insights and deep dive debugging of that model is something that has been missing for a long while, and is something that we wanted to address through the Responsible AI dashboard and toolbox. So let me show you a little bit what was our thinking behind the tool. I'm going to talk about this in the context of the Responsible AI Toolbox, which is a larger effort that we have started at Microsoft in order to build an open source framework for accelerating and operationalizing responsible AI with a set of interoperable tools, libraries, and customizable dashboards. Now, today we are going to talk mostly about the dashboards, and we hope that in the future we are going to have a larger conversation about the whole ecosystem. So, as many of you may be already aware of, there exist several dashboards that are already in our open source repository, which is the interpretability dashboard, the fairness dashboard, and the error analysis dashboard. And as I mentioned earlier, we noticed that there is a lot of connections between these problems on interpretability, fairness, and error analysis. And therefore, in the last 6 months, we have worked on building a single pane of glass, which is the Responsible AI dashboard that contains many of these functionalities together. And that's what we're going to demo later. The Responsible AI dashboard is customizable and modular, which means that you can customize the components of the dashboard according to your needs and the scenario that you're working on. It provides end-to-end fluid experiences, meaning that you don't have to sort of make up the data exchange between error analysis and interpretability. It just comes as a fluid experience. And with a click of a button, you can exchange data from one to the other. It's highly interactive, meaning that you can do all of this analysis by not getting out of the dashboard, just like clicking and deep diving through the same interface, and at the same time is usable together with machine learning code in Jupyter notebooks. So what do we really mean when we talk about customizable responsible AI workflows? As we see, there exist many components to the dashboard, but one may not need all of them for the particular scenario. One may, for example, be interested only in doing a particular workflow that goes from, so to say, error analysis in better understanding the errors, or moving on to data exploration and then causal decision making, if these are data and problems that are related to each other. Or they may even take a different path. They may go from fairness to interpretability and then data exploration. All this is customizable and possible through the dashboard. So today we are going to cover 2 areas that are supported in the tool: debugging machine learning models and responsible decision making. So let's first start with debugging machine learning models. I will first give an overview to what we see happening today when we try to improve our models and debug them. And please, take it with a grain of salt, in the sense that this is a high generalization about what is happening today. Many other practitioners may do something slightly different, but I want to contrast this approach with the approach that we are trying to bring in the Responsible AI Toolbox and dashboard. So very often today, what happens is that we train a model with data and perhaps with a certain architecture that we think is best for that data. We measure the error, and then we see, for example, whether we're happy with that error. And the way how we decide whether that error is sort of okay for the application often comes from comparing that error with papers that are already published in academia, if we are matching that type of performance, or if the customer is happy, or if we see that, for example, this type of performance is sufficient in overall or on average for that particular scenario. And if we're not happy, or if we think that there is room for improvement, there exist 3 different actions that may be folks take, such as, for example, adding more data, increasing the architecture size, or finding better parameters for that particular architecture and data. And then we compare this, we build a new model, we see what is the new error, and then we measure these two and see whether this has improved the situation. Now, this may sound all familiar and normal to a lot of people, but why isn't this sufficient, or why do we think that we can do better? Well, one of the main issues that we see with this process of just looking at one single score of error or one single score of accuracy is that this single score can hide important problems that may exist in the underlying model. For example, many of you may know that model performance is not uniform across the whole data set, and that there may exist different regions or pockets in the data, which later we are going to call cohorts, where the performance is much lower and the error rate is much higher. So, for example, there may be this cohort here that has a much lower performance, and for which perhaps the model or the system performance is not satisfying for the end user, or users may not even use it at all if they see this type of performance. So just measuring that error is not sufficient. And also, by not knowing where these errors are concentrated, it is very difficult to say how to fix that later, or how to mitigate a particular problem if it is not fixable. And different regions may fail for many different reasons. So in order to really, go through this process of improving the model, what we are trying to put into these tools is this other process where one goes from error identification by really characterizing what has happened, where is it that the model is not performing well, and then diagnosing it, basically understanding why has this error happened. There may be, tons of reasons of why the model is underperforming for that cluster. It may be because there is noise in the data, there may be noise in the labels, or it may be that the data is not balanced for that particular cohort. And we'll see some of these examples later on in the demo. And unless you really diagnose what the problem is, then you can go ahead and take different mitigation steps, such as balancing the data, or removing noise, or doing some feature engineering. We're going to give an example on this later on, but basically something that we want you to, at least one thing to take away from this talk, is this loop of model improvement, where one starts with error identification, detailed diagnosis, and then takes an informed step towards mitigation. And after that, maybe compare and validate the model to see whether the errors that were identified in the first place were actually mitigated. And there's a high-level picture here. I'm going to mention different tools that we have built. Basically, these are the building blocks that I showed earlier. Many of these are open source. Many of these address different parts of this model improvement lifecycle. And what we're doing with the dashboard, and there's a lot of work to do here, also in improving the dashboard for comparison and validation. But basically, this is the vision of like putting all this model improvement lifecycle into a single dashboard so that things can happen end to end. So with that said, I'm going to go through a quick demo. Basically, I am using the notebooks that are in our repository. This is the Responsible AI Toolbox repository that you can visit at your own time. And I'm using one of the notebooks that is already available there. And this is a problem that is doing house pricing prediction. And basically, we are transforming this problem to a classification problem. We're taking the median of the data, and what we're going to try to predict here is whether a house is going to sell for more or less than the median price for that particular data set. And if you're asking yourself, or how is this related to responsible AI? Well, you know, underestimating or overestimating the price of a house may have serious consequences, either for the company that is trying to do, for example, the appraisal of a house, or for the customer who is asking for a loan of the house and wants to have a fair appraisal on that particular property. So basically what you can do here is, this is just like the usual pipeline that you're building by splitting the data and having some trained data and test data for the problem. We are fitting a very simple model. In this case, it's an LGPM classifier with 5 estimators. And we are importing the RAI widgets package, which is basically the main package that offers this dashboard and the other dashboards that I showed earlier. And the important part that probably you have to be familiar with here is that, first of all, we're building up an object, RAI Insights, that takes as an input the model, in this case, the training data, the test data. It is telling the dashboard what type of problem it is, whether it's classification or regression. In this case, just for simplicity, we are going to look this from a classification lens, but regression is also supported in the dashboard, and you can call it as such. And then after that, we are customizing this dashboard and adding the components that we think are relevant to the problem. And since we're going to look at model debugging, we're going to add an explainer, error analysis, and counterfactual analysis for instance level debugging. After that, we are computing all the insights for this particular data set, and then we're showing the dashboard. So the dashboard has started in this local server, and let's look at all the components one by one. By the way, this is the list of components that we are going to look at in this demo, but of course it's possible to, you know, either delete one of these components or add another one, or even change the order of these components if you find that more comfortable for your scenario. The first component here is the error analysis component, and this is basically trying to understand where the errors are concentrated. In overall, we see that there is a 12% error rate on this particular problem, meaning that for 12% of the apartments and houses in the test data, the model is not able to predict whether that apartment is going to sell for more or less than the median price. Okay, so this sounds like, you know, a reasonable error rate. However, when we go down the tree here, and we are following the red paths here, because red in this case means that the error rate is higher than the base error rate, 12% in this case. If we follow these paths, we see that the error rate increases to 15% for apartments, for houses that have a greater living area that is more than 1,000 square feet, and even to 24% for such apartments that are older, so that they were built before 1978. So this is interesting. It means that our error rate increased by 2 times for this particular cohort. And since this is something that, you know, has twice an error rate. I'm going to save this as a new cohort. So all older houses that are larger than 1,000 square feet. So as an approximation. Now, there's other things, interesting things that one may see in this tree. For example, we can see that for every apartment that has a square footage less than 1,078, the error rate is really, really low. It means that we are probably set on this part, in that the model knows that what it's doing, and maybe we should focus on this one. Another thing you can do for error identification is looking at heat maps of different features. For example, I can look at, in this particular case, how is the overall quality of the apartment related, how does it relate to error? And we can see that, for instance, here, maybe I'm going to see at this particular area, I can see that when this overall quality is in between these values 4 to 7, which means that it is not exactly clear whether it's a good quality or a high quality, then the error rate becomes higher for these cases. Or I can look at, cross heat maps where I can try to combine the year where the house was built with the overall quality. So all this is possible, but this type of analysis with the heat map is more purposeful in that you kind of know what you're looking for. While for the tree, it is sort of using all these features in order to understand where the errors are concentrated. Okay, so we created this cohort, and in this particular node here. And now what we're going to do is to look at the other components. So basically, the next component is called model statistics, and you can look at the distribution of errors here and the type of errors in terms of like false positives and false negatives and prediction probabilities by cohort. And we can see that this is the cohort that we created earlier that was problematic. And we can see that when it comes to the false negative rates of this cohort are a lot higher, so 0.37 rather than 0.11, which is the false negative rate for the whole data, which means that perhaps for these older houses, our model is sort of underestimating the price of many of these older houses, which then causes the high false negative rates. And actually, by just looking at the counts here, we can see that this column here is almost as high as the column of false negative rates for the all data cohort, which means that almost all these errors, all these false negative errors, are focused on the older houses that are perhaps larger than 1,000 square footage. Okay, so this is a good information to have, and it is part of the diagnosis process, in that not only we identified errors through error analysis, but we also diagnosed them by understanding what type of error is happening here. So let's look at further diagnosis. We can look at how the data is distributed. The next component is the data explorer, and we're going to look at how the true Y is distributed, so the ground truth is distributed across this data. And for the whole data cohort, here we can see that the data is pretty balanced. And this is by definition because we are looking at the median value, and the median is basically in the middle, like half of the data is in one side, half is on the other side. However, when we look at this other cohort, the older houses, we see that the distribution here is a lot more imbalanced, meaning that it is not, the prior is not the same as for the whole data. And in fact, if I compare it with this other cohort here, so now I'm going to create another cohort for the newer apartments. I see that for this one, there is a lot of imbalance, but if the model always tells me that something very, very simple and tells me that the house is going to sell more than median almost always, then it is very easy for the model to get a good accuracy on this particular cohort, which is not possible for this one. And basically, this means that what perhaps I should do as a next step in order to mitigate this problem would be to either balance the data for this particular one in order, or to synthesize more data for this particular part of the cohort, so that I get a richer information about what does a house that is older and sells more than a median looks like. What is the richness of the feature space that will be able to tell me to help me to make this prediction. So this is one part of diagnosis. Another thing that one can do, again, on the diagnosis side, is to look at the importance of the features from an interpretability perspective. So basically here we're looking at how important each of the features is for each cohort in order to really understand the decision making of the model in this case. And we can also look at the directionality of how these features are important. For example, here we can see that the overall quality is important, but if the overall quality is higher than 7, then it is a positive contribution to the house being sold for more than median. And while this may sound intuitive, it is a very good tool for understanding spurious correlations. And what I mean by that is that sometimes you may be surprised. You may see that this directionality is totally on the wrong side, which means that the model is relying perhaps on a spurious correlation or a spurious dependency. Or you may be surprised and see that the model is using a feature that shouldn't be using from a fairness perspective. Like if this was a loan decision making, it might be looking at, say, things like race or gender, which it shouldn't be looking at in order to make that decision. So this was the interpretability component. And next, I'm going to pass it over to Mernush, who is going to talk to you in detail about what-if counterfactuals and instance-level debugging, if you are interested in debugging just a single prediction, and what happens afterwards. Mernush, I think you can take over.
Thank you so much. Perfect. So let me go to my slides and talk a little bit. There were lots of questions about whether the slides could be shared. We absolutely could make a PDF version of it and share with the organizers so that they can broadcast them. And I'm hoping that the meeting is being recorded and that will be shared with you as well. There were also 2 questions about which dashboard was being shown and whether it's open source. Yes, it is open source, github.com/microsoft/responsible-AI-toolbox. That's where we bring lots of our individual dashboards for fairness, interpretability, error analysis, etc. And now this one is called Responsible AI Dashboard. And so if you go to that GitHub repo, you will learn a lot more about it. But continuing on the amazing presentation that Bessa has started, one other factor that we wanted to bring to you for debugging your model is this notion of counterfactual example analysis, or looking at counterfactual explanations. And the way to think about this is this is a very powerful tool for both model debugging and decision making. And the way that it works is it can provide you with insights as what are the similar data points with different prediction outcomes from the model? Or in other words, what is the bare minimum change I could apply to a data point so that the model predicts a different outcome? And so I'll give you an example about that. It might be the case that my loan has got rejected, and the counterfactual to me is the same person, I mean, not the same person, same salary, same education, same marital status, same city. It's just that person has 20K less student loan compared to me, and that's why her loan has got approved, mine has got rejected. And so that's a very great tool for you to look into, come up with a handful of counterfactuals for each data point and take a look at that and get a sense for whether the model's predictions make sense. Obviously, if my counterfactual is someone with the exact same features but different gender or different ethnicity, you know that that's a major fairness issue. So that's a great tool for model debugging, but also sometimes I might go and ask, oh, my loan has got rejected by your AI. And I ask the bank, what could I do to get approval next time from your AI? And the same tool can really help you kind of like work on those features that you need to improve in order to get an opposite outcome from their AI next time. So that's the part that about decision making or taking action comes into the scenario. Now, the science behind this counterfactual analysis is powered by a library called DICE, which stands for Diverse Counterfactual Explanations. And it's model agnostic. It works for any machine learning model. It's state-of-the-art method for generating counterfactual explanations, and it can basically allow you to specify what factors the counterfactual module is allowed to change and in what range. For instance, you can't make someone younger, but you can always tell the counterfactual module that you can play with this person's salary in the range of plus 10K or plus 20K, which is something actionable the person could probably do by getting a promotion or other type of stuff. So I'm going to briefly show you the capabilities of counterfactual in the same example of housing. And so we can kind of take a look as how that can help. And so I'm not going to repeat the great flow that Bessa had, but I'm also clicking on bigger houses that are older, and I'll come to this counterfactual module. And what I am seeing right now is I'm seeing this particular scatter plot with all of the data points belonging to that erroneous cohort of old houses that were big or had a great above ground square footage. And I can click on any of these individuals. So this is a house that in particular have a high probability of getting a prediction of less than median, or it has been with a high probability, it has been predicted to sell for less than median. Something that grabs my attention is this chart, which tells me what are the top K factors that lead the most to the counterfactual for this data point. In other words, what factors of this house I should play with so that I get an opposite outcome from the model. And so you can see overall finish quality, great living room area, first floor square footage are the top three. I can also look at a handful of counterfactuals for this data point. So this is my original data point, and the dashes mean no change. So only if and these are counterfactuals. So only if this house had a finish quality of 6 to 8. So if I increase the overall finish quality of this house by 2 units, then the model would predict the opposite, which is actually this house is going to be predicted to sell for more than median. I can even do my own free-form counterfactual analysis. So what if this house was having a quality of 9 and an overall condition of 6, and I can save that as a new data point, and as you can see, it's moved from the opposite side of the diagram to the other. So now this house will have a higher overall condition and overall quality will be predicted to sell for more than median. So that's the conclusion to our debugging phase. So far, we've talked about how you learn more about your models, but sometimes you want to also inform your customers or inform your business stakeholders. And I talked a little bit about that with counterfactual because that can answer a lot of question of what can I do to get a different outcome from your model next time? But sometimes you just want to look at the historic data in order to come up with causal insights and see whether a particular type of factors or treatments have a causal impact on the real world phenomenon that you would like to move. And that's the part that we have brought to this dashboard by using one of the most known packages in the world of causal inference, which is called EconML. That is a package written in Python, which estimates individualized causal responses from experimental data. And in order for you to use this, you only need your historic data. There is no machine learning model here. You only need historic data, say in this particular example, the historic data of all the houses that have been sold in the past. And the real world outcome that I would like to touch is the housing price that this house will actually sell in the market, how much it's actually going to sell in the market. And the other thing that I need besides this real world outcomes and historic data is my treatments, what treatments I would like to explore the causal impact. And so say the number of fireplaces, the number of the square footage of the garage or number of garages, etc., could be the things that I have in mind in order to see whether if I build a new garage or if I add to the number of fireplaces in my house, would that have a causal impact on the housing price. So the causal inference will help you understand your overall causal effect, your individual causal effect, and also come up with a customized policy of what to do in your business. And let me show you a demo of that part. So this time, instead of activating, when I call the ARIA Insight, I'm not even passing a model to it. I'm just passing my historic data broken down to training and test. And now I would like to explore the causal. So I only add the causal module and I pass the treatment features. I care about how overall finished quality, number of fireplaces, garage cars, screen porch, square footage has an impact as a causal impact on the actual housing price. And my goal is to provide recommendation to either house developers or an individual house owner as what they can do to get a better price ask in the real market. And I load this dashboard again. So upon loading this, there are 3 different tabs that I see. The aggregate causal effect allows me to see how changing one factor that I have passed as a treatment would impact that actual housing price. So looking here, and this is in K, in 1,000 units, increasing the number of garage cars by 1 unit in all of the houses of this data set would on average lead to an impact of plus 20.2K on the overall housing price of this market. So overall, if I'm a developer with so many houses in the market, if I go ahead and add 1 more garage cars to each one, this is the average gain 20.2K that I'm going to see in the price bump. So that's that. You can look at others, and there are also confidence intervals as how much you would trust it, or you can trust that calculation. Before going to individual causal what if, I also go to the treatment policy, which is another factor where allows you to provide more generic policies for your business. So in my case, imagine I want to tell a developer as what is a custom policy they should incorporate in their development processes in order to see the biggest bump in the housing price in general. And so they ask me, okay, we are interested in understanding whether we should go ahead and add a screen porch to all of our houses. So one thing you can do is to go ahead and do it for all of your houses. Based on this analysis, you would get about 700 gain if you go ahead and increase the screen porch by 10%. But if you go with this custom policy, which says for houses with lower condition, lower finish condition, and smaller basement unit square footage, actually remove the screen porch. But if not, then expand it. Or for older houses that have a higher overall condition, you don't need too much to increase it. Actually go ahead and remove it. Otherwise, if there's a newer house in good condition, then increase it. And if you go with this custom policy, that's how much on average 2.1K gain on average you would see on all of your houses. This can become very handy when you're dealing with a marketing scenario or business scenario and you want to know how to treat your customers. Should you go ahead and provide discount to everyone? Should you go ahead and provide a promotion to everyone? Should you provide an incentive to everyone? Maybe the answer is if you do that, you're still going to see some bump. But if you go with the custom policy that we provide, that's where you will get the biggest bump. Finally, you come to the individual causal what if. That's when you want to provide an individual house owner as what to do in order to get the bigger ask in the market. And say I click on this particular house and I can see that if I tell the owner of this house that build 1 more garage cars or increase the finished quality of this house by 1 more unit, that's how much in K impact you would see. So if you increase the number of garage cars by 1 unit, you would see a 50K increase in the actual sales of this house. Or if you increase the overall finished quality by 1 unit, you would see 18.6K. And bear in mind that, of course, building a garage car or making your house having a higher finished quality comes at an expense. So you can balance this with that expense and make a decision as what to do in your specific case. And you can do causal what if. Say, what if I change the overall finished quality of my house to a bigger value? How that impact the actual outcome, and what is the confidence interval around it? So to summarize, this particular module allows you to use only historic data to take some real world decisions and impact your business, your customers, or your marketing department, whatever you're interested in. And alongside the other capabilities that were specific to model debugging, all of them are part of this effort called Responsible AI Dashboard. And Responsible AI Dashboard is one of the tools that exist under Responsible AI Toolbox. Responsible AI Toolbox is the bigger branding, holds bunch of individual tools, and this brand new Responsible AI Dashboard that we introduced. In the pipeline, we have a variety of different projects that are coming our way. We, first of all, plan to release a lot more data capabilities, data exploration, data mitigations, just so you can address more your model issues from the very get-go, which is the data. And we are integrating this in Azure Machine Learning, the web portal of that, which is Azure ML Studio and SDK, enabling on-demand generation of responsible AI insights by a no-code UI experience. We're also bringing our Fairlearn capabilities into this dashboard to make it really comprehensive, because right now, as you notice, there are signals that you can use in order to come up to understand the fairness of your model, but there are not sophisticated fairness metrics yet, and that's what we are going to release in the next version of this. We plan to integrate other components and flows into the MLOps story of Azure Machine Learning, just so you can incorporate it into your model lifecycle easily. Now, because there was also one question about collaboration, definitely feel free to reach out to us. We have started this in the open source with the sole purpose of bringing these to you in an easy manner, just so you can incorporate it into your current life cycle without any hesitation, but also for you to join our community, bring your own modules, plug them in, see how it works with the other modules, or just help us develop each of the currently existing modules further. And there are a variety of really greatly scoped projects that we can share, and we can work together on that. And we're truly hopeful that we can learn from you and hear from you and your interest in that manner. And with that, I'll pause, and I guess we will be very happy to answer some of the other questions that were asked in the chat.
So something that we're really passionate to hear from you is also your day-to-day experience in how you approach responsible AI. This is just one of the approaches. We want to learn more about how you are, solving some of these problems in machine learning prediction or in causal decision making. If there are any tools that you would like to share with us, and or if there are any needs that, for example, require a little bit more attention for your own practice.
Also, I just wanted to quickly show you, when you go to the Responsible AI Toolbox, we have introduction of what are all the tools underneath that, and then this Responsible AI Dashboard we just talked about is the brand new one. You can see the sample notebooks, and we just showed you this one for model debugging, and I also showed you this one for decision making of house improvements. And then there is a AKA links. If you go to aka.ms/RAI dashboard blog, that will take you to what we just explained. There's a step-by-step flow of it. We wanted to make sure that you have it in case you want to share with your colleagues, etc. So definitely recommend checking that out. And I also put it in the chat for you.
So there is a question by Michael of whether these libraries are available to be used outside of the AML proprietary system. Yes, so all the libraries, packages, the code on the dashboards, and the backing, machine learning libraries are all open source.
There is another question, how you define counterfactual. I'll explain it once more. I can explain it in two different ways. Counterfactual is, and maybe that slide is going to be helpful a little bit with a little visual. So can we still see my slides?
Yes. Yes.
Okay, perfect. So basically the counterfactual is about, you have an original data point, say this is Marnoush, and Marnoush's loan has got rejected. Then what counterfactual is showing me is what is the bare minimum change I can apply to Marnoush's features, bare minimum change. So like come up with the most similar person, very close to Marnoush, but like of course some tiny changes to her features, so that she receives an approval from the model. So this is my counterfactual closest to me in terms of the decision boundary. And this person has actually received loan approval. And the answer might be, oh, like that my loan has got rejected by the model. My counterfactual is someone who is earning 20K more annually, all other features remaining the same, or all features the same, that person has 10K less student loan. So it allows you to look at the closest data points with opposite outcomes. And that's a great way for you to debug your model and see, oh, Marnoush's loan has got rejected, but someone else with the exact same salary, same situation in terms of education and student loan and number of credit cards open whatsoever, only a different ethnicity has got approval. So that's why it's a great debugging tool to see whether the model is making sense. These data points, why they have received different outcomes. Is that based on factors that make sense or not? And it's also a great tool for providing advice to to users that, as I said, like, oh, Marnoush goes and she's very upset and she asks why your AI in the bank rejected my loan. And the bank says, oh, Marnoush, because of XYZ. And that bank looks at the top key important factors or local explanations. Now I ask, what can I do to get approval from this AI next time? What should I work on? And it says, oh, if you close 2 of your credit cards, then that's when you would get approval from our AI. So that's a great tool both for debugging and providing some actionable insights to end users.